All right, in today's lecture, we're going to cover the section 5.4 material on comparison tests. And there's two tests which we're going to look at in this section. The first of which is called the direct comparison test for convergence. And so here's what this test says. Let's suppose that we have two series, say a sum of terms a sub n and a sum of terms b sub n. And these will be two series which have positive terms. So there's two parts to this direct comparison test. The first says, if the values of a sub n are less than or equal to b sub n for all values of n, and the series b sub n converges, that is, the sum of the larger terms b sub n converges, then the sum of the smaller terms a sub n must also converge. So this sort of makes sense intuitively. If we're adding a bunch of terms b sub n together, and that sum is finite, it converges to some real number, then if we add together even smaller positive terms, it must also be convergent. Now the second part of this theorem says, if a sub n is greater than or equal to b sub n for all values of n, and the series b sub n diverges, that is, if the series of smaller terms b sub n is diverging to infinity, then the sum of the larger terms a sub n must also diverge. So this direct comparison test is sort of similar to the comparison test for improper integrals that we saw in chapter 3. If the sum of these larger values is converging, then the sum of the smaller values must converge. And if the sum of the smaller values is diverging, the sum of even larger values must also diverge. Now, a word of warning here, just like we had for the comparison test for improper integrals, if the larger series is diverging, we cannot make any conclusion about the smaller of the series. And similarly, if the smaller of the series is converging, we cannot make any conclusion about the convergence or divergence of the larger series. As we've got to be a little bit careful when we apply this, that we can actually make a conclusion about convergence or divergence. So before we look at some examples in this chapter 5 material, we're starting to learn a lot of different tests for determining whether a series converges or diverges. And one thing that we want to keep track of is, how do we know when to use a given test? So this comparison test we're going to use any time that we could try to compare our series to a p-series. So recall, a p-series is a series of the form 1 over n to the p power. So usually if we're working with a sum whose general term is a rational function, or like a quotient of two polynomials, or a quotient where maybe part of it looks like a p-series, that's when we might try to use this direct comparison test. So let's look at some examples of this. In our first example, part A, we're asked whether this series converges or diverges. We've got the sum of n cubed over n to the 8th plus n squared. So when we look at this series, we could maybe start by thinking about how to compare this to a p-series. So this is a quotient of two polynomials, and in my denominator, I have the sum of two polynomial terms. So let me ask myself, what would happen if I were to omit one of those terms in the denominator? So if I were to, say, omit this n squared term. So if I leave out the n squared in the denominator, I would be dividing by a smaller number for each term of my series, which would make each term larger. Dividing by less gives us a larger ratio. So the series that we have here is dominated by the sum from 1 to infinity of n cubed over n to the 8th power. If we just leave off that n squared in the denominator, we have the following. Now this series that I'm left with, if we simplify the general term a little bit, we have the sum from 1 to infinity. N cubed over n to the 8th leaves us 1 over n to the 5th power. And so this series that I'm left with on the end is a p-series. It's a p-series where the value of p is equal to 5. And recall the p-series test says as long as that power p is greater than 1, that p-series is guaranteed to converge. So if this larger series converges, then we're guaranteed that our original series, which was smaller, must also converge by this direct comparison test. So let's write out that conclusion. Let's explain exactly why our series converges. So we would say something like this. Since the series from 1 to infinity of 1 over n to the 5th converges, why does it converge? It converges by the p-series test with a value of p equal to 5, which is greater than 1. That's the condition we needed for convergence. So since that series converges, then the given series must also converge by the direct comparison test. So here our result is that this series converges by the direct comparison test. We're noticing in this chapter 5 material, when we're testing series for convergence or divergence, our solution is usually a sentence statement like this. We have to prove why the given series that we're considering is convergent. So our answers usually are some sort of sentence or written statement that explains why we know our series converges. So we always want to be sure in these problems to state the name of the test we're using, and if we need to guarantee convergence of any other series that we're comparing this to, we need to state which tests we're using to get convergence of those series. So let's look at some other ones, get a little more practice with this. In part B, we have the sum from 2 to infinity of 2n over the square root of n to the 5th, and this should be a plus n instead of minus n. I had made a typo in the notes there. So again, we see that this series is sort of similar to a p-series. It's got a quotient of different powers of n. And as in the last example, I see that in the denominator, under the square root, I have the sum of two terms, n to the 5th plus n. So I could ask myself, well, let's see if we could compare this to a p-series. So as in the last example, if I were to omit one of these terms in my denominator, say if I got rid of the plus n, then I would be dividing by a smaller number, which would give me a larger term for my series. So the series that we're given is dominated by the series n equals 2 to infinity of 2n over the square root of n to the 5th power. Now, this series that I'm left with, let's see if we could simplify it a little bit. So here we have the sum from n equals 2 to infinity of 2n divided by the square root of n to the 5th. Well, that's the same as n to the 5th raised to the 1/2, or n to the 5/2 power. And then if I simplify this a bit further, I can cancel one factor of n on top and bottom. and I'm left with 2 over n to the 3/2 power. So this simplified series that I'm left with is a p series, where the power of p is equal to 3/2, which is greater than 1. So I know that this series converges. Therefore, this smaller series that I was given must also converge by that direct comparison test. So let's write out our justification here. We could say, since the sum from 2 to infinity of 2 over n to the 3/2 power converges by the p-series test, where the value of p is equal to 3/2, which is greater than 1. The given series converges by the direct comparison test. So here our solution is that this given series converges by direct comparison with a convergent p series. So let's look at some other ones. In our next example, we have the sum from 2 to infinity of 1 over the natural log of n. So this looks sort of similar to a p series, but the only difference is, instead of having a power of n in our denominator, we have the natural log of n. Now, the natural log of n can be compared to n directly, and this is the first time we're going to see this comparison for series. So let's see how exactly this works. It's a little bit tricky, but if we think about a geometric argument, we can see how the natural log of n compares to n. So let's think about the graphs of those functions. If we were to consider the natural log of n and n as a function of n, let's look at their graphs. So the natural log of n is defined for positive values of n, and our graph looks something like this. It's increasing without bound, but the rate at which it's increasing is decreasing. That is, it's a concave downward graph. And if I were to consider the graph of y equals n, well, we have a line of slope 1 and y-intercept 0. And so this is the graph of n itself. So we can see from the graphs of these functions that the graph of y equals n is always greater than natural log of n. So comparing our graphs, we know that n is always greater than the natural log of n. Now, in our problem, we're working with the reciprocal, 1 over the natural log of n. So if I were to take the reciprocal of both sides, I would need to reverse my inequality. That is, 1 over n is less than 1 over the natural log of n. So if I think about the series that I have, the sum from 2 to infinity of 1 over log of n, well, this is dominating the series from 2 to infinity of 1 over n, since 1 over natural log of n is always greater than 1 over n. But this series from 2 to infinity of 1 over n is a p series where the power of p is equal to 1. That was called the harmonic series, that special series where the power of p was equal to 1. And we know from the p-series test, or the integral test, that that series diverges. So then the larger series that we were given must also diverge. So let's write out our justification here. We could say since the sum from 2 to infinity of 1 over n diverges by the p series test, where the power p is equal to 1, the given series also diverges by the direct comparison test. So here, our conclusion is that this series 1 over log of n diverges by comparing it with the harmonic series 1 over n to the first. Okay. So anytime that we have a quotient involving that natural log of n, say it was like natural log of n quantity squared, well, we could compare it by looking at the smaller series 1 over n squared. So let's look at some other ones. In this next example, part D, we've got the sum from 1 to infinity of cosine n plus 3 over n cubed. So when we look at this one, we see it's pretty close to a p series. It looks almost exactly like 3 over n cubed. However, I have this extra cosine of n term in the numerator. So let's think about how we could compare this series with the p series 3 over n cubed. Now we know 3 over n cubed would be converging by the p series test, since the power of p would be 3, it's greater than 1. So if I want to use the direct comparison test, I want to show that this series is smaller than something related to a p series of the form a constant over n cubed. So to make this expression even larger, I could think about the maximum value that cosine of n could take. I know that cosine of n lies between plus and minus 1, so the largest value that we could ever have for the terms of this series would be 1 plus 3 over n cubed, or of course this is the same as 4 over n cubed. And so this series that we have here is a p series where our power of p is equal to 3. It's greater than 1, so we know that this series converges, which means that the given series, which was even smaller, must also converge. So let's write out our justification here. We would say since the sum from 1 to infinity of 4 over n cubed converges by the p series test with a value of p equal to 3, which is greater than 1, then the given series also converges by the direct comparison test. So here we have convergence by comparing our series with a known convergent p series. So let's look at another one, sort of similar. In this next one, part E, we have the sum from 1 to infinity of 4 plus sine of n over the square root of n. Now this one is sort of similar to that last problem. It's almost exactly like the p series 4 over the square root of n, which we know would be a divergent p series, since our denominator would be n to the 1/2, or the power of p is less than 1. The only difference here is that we have this extra sine n term in the numerator. So if we want to compare this with 4 over n to the 1/2, or a p-series of the form of constant over n to the 1/2, well, we know that series diverges, so we need to show that this series is even larger than the series that we're comparing to. So in this example, we would want to make sine of n as small as possible, so that this series would be larger, and we could get a result from direct comparison test. So here we could look at the sum from 1 to infinity of 4 plus the smallest value that sine of n can ever be is -1. We know sine of n oscillates between positive and -1. So to get the smallest value, we would take its minimum value of -1 over root n. Or of course, this is the same as the sum from 1 to infinity of 3 over the square root of n, which is a p-series. Here the power of p is 1/2, since we're talking about the square root of n. So since that power is less than 1/2, this p-series diverges, which means that our given series, which was even larger, must also diverge. So let's write that out. So here we would say, since the sum from 1 to infinity of 3 over the square root of n diverges by the p-series test with a value of p being 1/2, which is less than 1, then the given series also diverges by the direct comparison test. So here we would have that our series is diverging. All right, so let's look at some other ones. In this next example, part F, we have the sum from 1 to infinity of 2 over 3 to the n plus n. So this term, or this series, looks sort of similar to the p-series 2 over n. So if we were to compare with that p-series, we see the extra term that we have here is this 3 to the n in our denominator. So if we were to get rid of that 3 to the n term in the denominator, that is, if I divide by a smaller number, I would get a larger series. So the series that I'm given, we could say, is dominated by the sum from 1 to infinity of 1 to infinity of 2 over n to the first power, which is a p-series. Where my power of p is equal to 1. So that is the harmonic series, which we know diverges. So here, if the larger series diverges, then remember, I can't make any conclusion about the convergence or divergence of the smaller series. I would have to know that the larger series is converging. So here, based off the comparison that I started with, the direct comparison test gives no conclusion. But maybe I could compare my series not with a p-series, but with a different type of series which we could determine convergence for. So let's consider the series that we started with. That is the sum from 1 to infinity of 2 over 3 to the n plus n. And instead of omitting that 3 to the n term in our denominator, let's omit the plus n term. So if I were to get rid of the plus n term in my denominator, I would be looking at a larger series of the form 2 over 3 to the nth power. Or if we rewrite that a little bit, this is the sum from 1 to infinity. I could think of this as 2 times 1/3 to the nth power. So this series that I'm looking at is a geometric series, where my value of a is equal to 2 and the ratio r is 1/3. Now recall, for geometric series, to determine convergence or divergence, we look at the absolute value of the ratio. And in this example, we have our ratio is 1/3, which is less than 1. So since the absolute value of that ratio 1/3 is less than 1, the series that I'm comparing to, that is the sum from 1 to infinity of 2 times 1/3 to the nth, converges by the geometric series test. So then my smaller series that I was starting with must also converge by the direct comparison test. So we can say then the given series also converges by the direct comparison test. So here we have convergence. All right. So this last example illustrates that maybe if we initially try to compare with a p-series, we might not have the right direction of an inequality to determine convergence or divergence of the original series. So maybe we could try to compare with something else, like say a convergent geometric series. So let's look at another example. In part G, we have the sum from 3 to infinity of n square root of n over 8n squared plus 6n. And we want to see if this converges or diverges. Now we see it's sort of similar to a p-series. It involves a quotient of n raised to different powers. And so we see that our denominator here is a sum. So we could ask ourselves, well, what happens if we omit one of these terms in the denominator? Maybe if I omit the 6n term, what would happen? So if I leave out a term in the denominator, I would get a series which is larger. So here we would have n root n over 8n squared is what we're comparing with. Or if we simplify this a little bit, we have the sum from 3 to infinity. Our numerator is n square root of n, or n to the 3 halves. My denominator is 8n squared. So canceling n to the 3 halves power on top and bottom, I'm left with 1 over 8n to the 1/2, which is a p-series, where the power of p here is 1/2, which is less than 1, so that series diverges. So here, my smaller series, I can't make any conclusion about. Since the larger series diverges, I don't know anything about convergence or divergence of the smaller series here. So in this first direction of comparison that we tried, we could say that our direct comparison gives no conclusion. So we could try to compare with something else, as we did in that last example. So again, let's consider the sum from 3 to infinity of n square root of n over 8n squared plus 6n. And instead of omitting the 6n term, let's omit this 8n squared term. So if we omit a term from our denominator, we get a series which is even larger. Here we would have the sum from 3 to infinity of n square root of n divided by 6n, which simplifies to the sum from 3 to infinity. Canceling an n on top and bottom, I have the square root of n over 6. And this series that I'm comparing with above diverges. Why does it diverge? Well, it diverges by the test for divergence. We see for this general term, square root of n divided by 6, as n gets larger, this general term increases without bound. It's not converging to 0. So here we could say diverges by the test for divergence. Remember that test said if you take the limit of your general term as n approaches infinity and you get anything other than 0, then that series diverges. So again, if the larger series diverges, we can't make any conclusion about our smaller series. So even with this other comparison, again here, our direct comparison gives no result. So in this last example, part G, we're seeing that we have no conclusion. If we're trying to apply the direct comparison, we don't have the correct direction for our inequality. So there are some series like this one where the direct comparison test cannot be used for convergence or divergence, but there is another test which we'll discuss in this section, which can be used to determine convergence or divergence for such series. So this next comparison test that we will talk about in section 5.4 is called the limit comparison test, which says the following. If we have two series of terms a(n) and b(n), and they are series with positive terms, then we would look at the limit of the ratio of these terms, a sub n over b sub n, as n becomes infinitely large, and let's say that that limiting value is some number L, where the value of this limit L lies between 0 and infinity, then this test says that either both series converge or both series diverge. So this limit comparison test we might use if the direct comparison test fails, but we suspect that our series behaves similarly to some p series whose convergence or divergence is known. And the way that we're going to apply that test is to look at the limiting value of the ratio of terms a(n) over b(n). So what this test says is if we're looking at large values of n and that ratio of terms, a(n) divided by b(n) is some number between 0 and infinity, that means that these two terms, a(n) and b(n), grow at approximately the same rate for large values of n. So that means that our two series, the series of a(n) and b(n), behave the same way for large values of n, so they would both converge or both diverge. So we would use this limit comparison test if we're trying to compare our series with a p series, but direct comparison fails. So in this next example, part A, we're going to consider the problem we were just looking at, the sum from 3 to infinity of n square root of n over 8n squared plus 6n. And we said, well, this behaves sort of similarly to a p series, or it looks kind of like a p series. And how do we know which p series we're supposed to compare with? So the general rule for determining what you're going to compare with is to look at the ratio of the highest powers of n in your numerator and denominator. In this case, our numerator is n to the 3/2, and we're dividing by 8 n squared. So if we were to consider that ratio of the highest powers of n, let's try to compare with the sum, say from 3 to infinity, of n to the 3/2 over n squared, which would simplify to the sum from 3 to infinity of 1 over the square root of n, which we know is a p series which diverges. So to use this limit comparison test, I'm supposed to take the limit as n approaches infinity of the ratio of the terms of my series. So here, if we call, maybe to make the notation a little bit easier, let's call this first term a sub n, and the term for the series I'm comparing with b sub n. So if we're looking at the limit of the ratio a sub n over b sub n, we have the limit as n approaches infinity of, well, a sub n was n square root of n divided by 8n squared plus 6n. And then we're dividing by b sub n, which is 1 over the square root of n. Now here, to divide fractions, we know that we're supposed to multiply by the reciprocal of the denominator. So here we would have n square root of n over 8n squared plus 6n times the reciprocal of our denominator is square root of n over 1. So this gives us the limit as n approaches infinity of, simplifying our numerator, we have n squared divided by, in the denominator we had 1 times 8n squared plus 6n. So now what we're left with is the infinite limit of a rational function where our numerator and denominator have the same highest power of n. So the limiting value is the ratio of the coefficients for those highest powers, in this case 1/8. Now this limiting value that we have of 1/8 is a number between 0 and infinity. Remember, for this limit comparison test, whatever our limiting value is must be between 0 and infinity to get a conclusion. Now our conclusion here is that both of these series converge or that both diverge. So which one is it? Well, the series that we were comparing with, this series of 1 over square root of n, is a divergent p series. So the series that we're given must also diverge by this limit comparison test. So let's write out our justification here. We could say, since the sum from 3 to infinity of 1 over the square root of n diverges, by the P series test with the value of P being equal to 1/2, which is less than 1. The given series diverges by the limit comparison test. So here we were able to show that this series diverges using the limit comparison test, but we saw in that last example the direct comparison test failed. So in general, this limit comparison test is a little more powerful than that direct comparison. So let's look at some other examples of this. In our next one, part B, we've got the sum from 1 to infinity of this quotient of two polynomial terms. So here we could make use of a limit comparison test. Now let's think about what P series that we might try to compare this to. So I mentioned earlier that we might look at the highest power of n that appears in our numerator and denominator. And here it's a little bit tricky. We see our denominator has this polynomial term cubed. So if we were to rewrite our series first, we have our numerator is n squared plus 5n. And if we were to expand that term in the denominator, the highest power of n is going to be, let's see, an 8n cubed, and then plus some smaller power terms. So looking at the ratio for the highest power on top and bottom, we have an n squared over 8n cubed. So n squared over n cubed would be 1 over n to the first. So let's compare with the sum from 1 to infinity of 1 over n to the first power. That is the harmonic series, which we know diverges. So here, if we're applying the limit comparison test, we're going to look at the limit as n approaches infinity of the ratio of our terms. So our first term for the given series was n squared plus 5n all over 2n plus 1 quantity cubed plus 2n. And then we divide by 1 over n to the first, or equivalently multiply by its reciprocal, n to the first over 1, which gives us a limit as n approaches infinity, multiplying my n to the first through to the numerator. We have n cubed plus 5n squared all over. Again, if we expand our denominator, we have something of the form 8n cubed plus some other terms involving smaller powers of n. So looking at the ratio of those lead coefficients, we have the same highest power on top and bottom. So for this infinite limit, we would have a value of 1/8, which does lie between 0 and infinity. So we know that both series converge or both diverge, and the series that we were comparing with was the harmonic series, where P, or the P series where P is 1, which we know diverges. So we could say, since the sum from 1 to infinity of 1 over n diverges by the P series test with a value of P equal to 1, the given series also diverges by the limit comparison test. So here we're getting divergence. All right, so let's look at some other ones. In this next example, we have the sum from 1 to infinity of 1 over 4 to the nth minus 3n. So here we could maybe initially try a direct comparison. We see that this is sort of similar to a geometric series, 1 over 4 to the nth, but we're subtracting 3n in the denominator. So if I divide by less, if I'm subtracting something from the denominator, I would have a larger series than if it weren't there. So I could think about a direct comparison with 1 over 4 to the n, which is a geometric series. I could rewrite this as 1/4 quantity to the n. So this series that I'm looking at on the end is geometric. And the value for the absolute value of the ratio r is 1/4, which is less than 1. So this geometric series is converging, but since the series that I'm given is larger than that, I can't make any conclusion using a direct comparison. So instead, let's try to use a limit comparison by comparing with this same geometric series. So here, let's try to compare with the sum from 1 to infinity of 1 over 4 to the nth power, which we know is a convergent geometric series. So using our limit comparison test, we would be taking the limit as n approaches infinity of our term for the given series, 1 over 4 to the n minus 3 times n, and then we would divide by 1 over 4 to the nth, or equivalently, multiply by 4 to the nth over 1. So we then have the limit as n approaches infinity of 4 to the nth over 4 to the nth minus 3n. So as we're taking the limit as n approaches infinity, we get an indeterminate limit of the form infinity over infinity. So we could apply L'Hopital's rule, and we would have the limit as n approaches infinity of the ratio of the derivatives of our numerator and denominator. So for our numerator, remember to differentiate these exponential functions like 4 to the nth. We would have 4 to the nth power times the natural log of our base, 4. So for our denominator, we again had 4 to the nth. Its derivative is 4 to the nth times log of 4 minus 3. So again, we would have an infinite limit, or an indeterminate limit of the form infinity over infinity. So if we were to apply L'Hopital's rule again, we have the derivative of 4 to the n is 4 to the n times the natural log of 4. And then we already had a factor of log 4, so we get log 4 squared. And then our derivative for the denominator is the same. And then the minus 3 has a derivative of 0 now. So we're left with the limit of this ratio, which we've got the same expression on top and bottom, so we have a limit of 1. Which of course lies between 0 and infinity. So the limit comparison test says that both these series converge or both diverge. And here they both converge. Let's write out our justification. Since the series 1 over 4 to the n converges by the geometric series test, where we're looking at the absolute value of r, which would be 1/4, which is less than 1, then the given series also converges by the limit comparison test. All right, so here we have convergence, again, using the limit comparison test. So let's look at another one. In this next example, part D, again, we have a series whose general term is a quotient of terms involving different powers of n. So we might try to make use of a comparison. And here, there's not a clear direct comparison to work with. So let's try to make use of a limit comparison. And to determine what we're comparing with, we're going to look at the highest powers of n on top and bottom. So in the numerator, we have n to the 4th. And in the denominator, we have the square root of n to the 10th for our highest power. Now the square root of n to the 10th would be n to the 5th power. So we're looking at something of the form n to the 4th over n to the 5th, or 1 over n. So we might try to compare with the series from 1 to infinity of 1 over n to the 1st, which we know is the harmonic series which diverges. So to use this limit comparison test, we take the limit as n approaches infinity of the ratio of the term of our series, which was n to the 4th minus n cubed plus 1, over the square root of n to the 10th minus n to the 6th plus 3. And we divide by the general term that we're comparing with, 1 over n, which is equivalent to multiplying by its reciprocal, n over 1. So we have the limit then, as n approaches infinity, distributing the n through our numerator. We have n to the 5th minus n to the 4th plus n over the square root of n to the 10th minus n to the 6th plus 3. So now, taking this infinite limit of the ratio of these terms, well, we see that we have a ratio of terms where we have the same sort of highest power on top and bottom, n to the 5th divided by the square root of n to the 10th, which would be n to the 5th. So as n approaches infinity, here we would have a limit of 1, since the ratio of those terms is 1 over 1. And this limit, of course, lies between 0 and infinity. So both of these series converge or both diverge by the limit comparison test, and the one that we were comparing with, the harmonic series, we know diverges. So let's write out our conclusion here. Since the sum from 1 to infinity of 1 over n diverges by the p series test, with a value of p being equal to 1, the given series diverges by the limit comparison test. Okay. So in our last example, we have the sum from 1 to infinity of sine of 1 over n squared. So here, maybe we could, it doesn't initially appear that we might want to use a comparison test. So let's think about some of the other tests which we've considered. A lot of times the first thing that we want to try is the test for divergence. So here, if we were to look at the limit as n approaches infinity of our general term, we see that as n gets large, 1 over n squared is approaching 0. So we get a limit of sine of 0, which is 0. So here the test for divergence fails. If we had something other than a 0 limit, we could say this series diverges. But since it's 0, we don't know if it converges or diverges. Now, we can see pretty clearly that it is not a geometric series. It doesn't have the correct form. It is not going to be telescoping. There's no way to rewrite this such that the internal terms will cancel. And if we can avoid it, we want to avoid the integral test at all costs, since that's one of the more difficult tests to apply. So the only other tests which we have are a direct or limit comparison. And there's not really a good comparison here directly with a p-series. But we could consider the limit comparison test, and let's think about what we might want to compare with. So here we're taking sine of 1 over n squared. Now, if it were just 1 over n squared, then we would have a convergent p-series. So let's maybe try to compare this with that series. So let's start by saying let's compare with the sum from 1 to infinity of 1 over n squared, which we know is a convergent p-series. So this limit comparison test says we take the limit as n approaches infinity of the general term for our series, which was sine of 1 over n squared. And then we are dividing by our general term, 1 over n squared, or equivalently, we're multiplying our numerator through by n squared. So we would have n squared times sine of 1 over n squared as n approaches infinity. So here we have another form for an indeterminate limit. This first term in our product, n squared, as n approaches infinity, is becoming infinitely large. And we said that as n approaches infinity, this second term, sine of 1 over n squared, is approaching 0. So this is an indeterminate form. So to handle this, we want to try to make use of L'Hopital's rule. But to use L'Hopital's rule, we have to have something of the form 0 over 0 or infinity over infinity. So this one we could rewrite in the original form that we had it. That is sine of 1 over n squared divided by 1 over n squared. And here, as n approaches infinity, both our numerator and denominator are approaching 0. So we have a form here where we could apply L'Hopital's rule. So L'Hopital's rule says that we look at the limit of the ratio of our derivatives. So the derivative of our numerator, the derivative of sine of a function, is cosine of that function, 1 over n squared, times the derivative of the inner function. Now the derivative of 1 over n squared, or n to the negative 2, is negative 2 n to the negative third, or negative 2 over n cubed. And then we're dividing by, the derivative of 1 over n squared, we just found as negative 2 over n cubed. So this factor of negative 2 over n cubed on top and bottom cancels, and we're left with the limit as n approaches infinity of cosine of 1 over n squared. Taking n as larger and larger values. 1 over n squared is approaching 0, and cosine of 0 is 1. So our limit lies between 0 and infinity, which means that both series converge or both diverge. But the one that we were comparing with was a convergent p series. So this series will converge. And let's write out our justification. We would say, since the sum from 1 to infinity of 1 over n squared converges by the p series test with a value of p equal to 2, which is greater than 1, the given series also converges by the limit comparison test. So we're seeing from this last few examples, when we're making use of the limit comparison test, we sometimes have limits of indeterminate form, and we're required to use Hopital's rule. So it may be beneficial to go back and review some of your Calc 1 notes on evaluating limits of these indeterminate forms using Hopital's rule. We've seen that come up a couple of times when we're applying this